So let's recall the inverse function theorem. We recall this is the entire point of section 6.8. This was the last thing I wrote down at the end of lecture 6.8.3. So now let's see exactly how much of the proof we can actually write down. And you've actually done a lot of the proof. I've done some of the proof. So let's recall what you did last time in homework 26. There is a positive number delta such that f is 1-to-1 and on the ball centered at C of radius delta, and df of x, not of C of x, is invertible. For all x in this ball. So then we're going to just let U be that ball centered at C of radius delta. And then we've got U is a subset of X if delta is small enough because X is open. C is certainly in U. F is 1-to-1 on U, and U is open. So now we just need to show that f of u is open and f inverse is continuously differentiable. So by the lemma in lecture 6.8.2, yeah, that was most of that lecture, parts 2 through 4. We have that if omega is an open subset of U, then f since df of x is invertible everywhere in omega, f of omega is open. And that gives us two things. Let W equal f of u. We can just take omega equals all of u, then, and that gives us that f of u is open. So that takes care of this piece of the inverse function theorem. And now here's our next piece. Let's let G equal f inverse. So G is a function whose domain is W, whose range is U, is bijective. And then if omega is a subset of U, is open, then let's say G inverse of omega. That's the set of all x in W such that G of x is in omega. But G of x is in omega. G of x, that is the set of all f of y such that y is in omega. If y is in omega, then y is in u, so y is G of x for some x in W, and therefore that x must be in G inverse of omega. You can trace through the pieces. We just get f of omega. This thing is open. So we see that the inverse image of all open sets are open. So G is continuous by our favorite theorem from the section on continuous functions. So we know that G is continuous. Now let's remember your homework 25. This is a little bit older. We've got that U and W are open subsets of RP. We've got F and G are inverses between these open functions. And we've got that F is continuous. That's because F is differentiable. That's by theorem 6.7a as usual. And we just saw that G is continuous. And we've also got that df of x is invertible. For all x in U. And this is the setup for homework 25, specifically for part C of homework 25. So by homework 25C, if all of those conditions are satisfied, G is differentiable. At f of x for all x in U. And because F is a bijection, this means that dg of y, G is differentiable at y, dg of y exists for all y in W. So that gives us that F inverse is differentiable. Now all we need to do is we need to prove that dg of y is continuous. And we remember by lemma in the lecture, first lecture in this section, although I started it with some matrix theory, we have that dg of f of x is equal to df of x inverse or you can put it another way, dg of y is equal to df of g of y inverse. So we just need to show that if df is continuous, df inverse is continuous too. So here's what we're going to do. Let's let y and z both be in W. And let's let A be df of g of y, and then b is df of g of z. And then we want to know how far apart A inverse and B inverse are. Let's notice that they are both invertible linear transformations from Rp to Rp. Invertible linear transformations, invertible linear functions. Now let's let V be a vector. And then A inverse of V minus B inverse of V, we can write that, I'm going to write that as A inverse of V minus A of A inverse of B inverse of V. So, sorry, I've got sorry, I said one too many A inverses, but because A is linear, A inverse is linear. The inverse of a linear function is linear, so we can distribute it. We get A inverse of V, and then the A and the A inverse cancel out. And now I'm going to want to move a B inverse out. So we've got A inverse, and then I'm going to turn V into just B of B inverse of V minus A of B inverse of V. And then we can break that up into A inverse of, and then B minus A, remember, is a linear operator, and then we write B inverse of V. And now let's write some estimates on this thing. So the norm of A inverse V minus B inverse V, that's less than or equal to the norm of A inverse times the norm of whatever it is we feed into A inverse, which is just B minus A of B inverse of V. Remember, this is how the operator norm of A inverse. The norm of A inverse is a constant such that A inverse of some expression, okay, it's a huge mess, but it's nonetheless a vector, is at most the norm of A inverse times the norm of that vector. And then we just do this 2 more times. We get the norm of B minus A. That is a linear function, so it has a norm. And then we get the norm of B inverse. And then we get the norm of V. So A inverse minus B inverse is a linear transformation. And we can write down an estimate on its norm, A inverse minus B inverse, less than or equal to the norm of A inverse times the norm of B minus A times the norm of B inverse. Let's put this all back together. We have that the norm of, remember, A was df of g of y, so A inverse is dg of y. So we get that the norm of dg of y minus dg of z. That's the norm of A inverse minus B inverse. Run all this stuff through. Norm of A inverse, that's the norm of df of g of y inverse. And then we get our norm of df of g of y minus this df of g of z. And then we get our df of g of z inverse the norm of that. So now we'll do an epsilon delta continuity argument. We pick an epsilon greater than 0 and and now something else which you proved in homework 26, which sort of got added to homework 26 while I was making this video. There is a positive number lambda, a finite number lambda, such that this norm, the df of x inverse is less than or equal to lambda for all x in u. So of course that's going to be true for g of y and g of z in particular. And let's also go look at a particular y in w. So df is continuous at the point we're looking at our particular y. We're showing that dg is continuous at y. So df is continuous at g of y, which remember is in u, since f is continuously differentiable. So there is a zeta greater than 0 such that if x minus g of y, if that distance is less than zeta, then df of x minus df of g of y is less than, now we'd like epsilon over lambda squared. Let's add a 1, and just so we don't have to worry it. Yeah, I don't think lambda can possibly equal 0, but we might as well put a 1. And now g is also continuous, so there is an eta greater than 0 such that if the distance from z to y is less than eta, then g of z minus g of y is less than r zeta. So put it all together. So if z is in w, z minus y is less than eta, then g of z minus g of y is less than zeta. So that means df of g of z minus df of g of y, that thing is less than epsilon over lambda squared plus 1. So we have that. Our dg of y minus dg of z is less than, we've got a lambda, we've got an epsilon over lambda squared plus 1, we've got another lambda, it's less than epsilon, so dg is continuous at y for all y in W, and that shows that G is continuously differentiable, and that completes the proof of the implicit function theorem. So here is the inverse function theorem. We've finally proven this. We've proven that if X is an open subset of RP, well, that's easy to check. And you've got a function f mapping from X to RP. Then if your function is continuously differentiable and df of c is invertible, then we have all these nice properties. So I think I'll finish up section 6.8 by talking a little bit about when are these properties true. How can we recognize functions f that satisfy these conditions? So first off, let's recall theorem 6.5.9. So this says that if X is an open subset of RP, like we've got in this situation, f is a function in theorem 6.5.9 maps into RQ, but let's go ahead and restrict to f mapping into RP because we only really care about implicit inverse function theorem at the moment. And partial k of f sub j, that's the partial derivative of the jth component of f in the xk direction. If that exists at the point x, so partial afk x is open, remember, for all x in x and all j between 1 and p, also k between 1 and p. And if c is in x and all of the partial k fj's are continuous at c, then df of c, that exists. And now we can actually strengthen this. So here is an exercise, which may show up on your homework or your third exam. If partial k fj is continuous everywhere in x, for that whole range of j's and k's, well, theorem 6.5.9 tells us that df of x exists for every x for every x in x because the partial derivatives are continuous at x. And this is the exercise part. The function df, whose input is x and whose output is linear functions from Rp to itself. Or you can prove this for linear functions from Rp to Rq, is also continuous. So that's a thing to check. So that's one way to see easily whether a function f is indeed continuously differentiable. Checking to see if df of c is invertible is actually much more straightforward. We don't need it to improve on anything we already know what to do. This says that Theorem 6.5.7c says that under the conditions of Theorem 6.5.9, x is open and all the partial derivatives are continuous. We have that df of c of the vector x, you can write that as a matrix. So you start with partial 1 f1 of c. You go across to partial p f1 of c. Then next row, partial 1 f2 of c, partial p f2 of c, all the way down partial 1 fp of c. Cross partial p fp of c. And then that whole thing gets multiplied by the vector x1, x2, down through xp. So all of you who remember your linear algebra, of course. So df of c is invertible if and only if there's our linear algebra trick for checking whether a matrix is invertible. It's just you take the determinant of the matrix, partial k f sub j of c, for the matrix which has a partial k f j of c as its entries, if that determinant is not 0.